briefly, 10 minutes probably go through what one of my students is doing actually in this. So we'll talk about the smart grid. We'll talk about we'll talk about how to do the stability analysis. And then one other aspect about power system is the power quality. So this one of my students actually is working on. And he prepared this slide for me. I didn't prepare slides. So essentially the same thing. We've seen this for a long time. So a few days. So common DC bus. What's really happening? You have a lot of power converter connected to this DC bus, and then how you can minimize the harmonics, on this common DC bus. This is something we want to do. The test rig, we seen this one. From Figao, I presented yesterday, but this is something we are going to do is to disassemble what Figao has done, just put it into the cabin. Essentially, you got the grid power supply, and then connect to 3 converters, and then to the common DC bus, and afterwards, common DC bus, you have the DC chopper, you have the battery, you have the resistor. To connect to this as a load bank, to connect to this common DC bus. So this thing is not ready yet. It's going to be ready probably March or April next year. The communication channel, what we discussed yesterday, I said on comments that for large scale communication, it's not really good to do analog signals. So here we're using the CAN bus. So we've spent quite a lot of money on the NI product. Cost us probably 30K probably to get these devices. So we're going to use it and then do the communication essentially. We'll start from simple system. We have start from back-to-back converter essentially, and then we do some neat review on what is going on about in terms of harmonics cancellation on the DC bus. What's really studied so far. I think the battery. Yeah. What's been studied so far is the either you have a multi-phase machine, which means the frequency are the same, okay, or you have this kind of topology. Still, you have the same fundamental frequency. Essentially, for the sources wise, you always have the same frequency, okay, for the fundamental. And then you use centralized control technique as well, okay, which means all the control is centralized. But for aircraft application or for the microgrid application, one of the ideas is we are going to move away from the fixed frequency to a variable frequency. So which means the 400 Hz or on the aircraft side will be from 300 Hz to 800 Hz fundamental, and how you can handle this. And this is what we have been doing. We'll start from very, I think we're quickly jump through now, I think, because there's some time limit. So what we do, we start from analyze of the single two-layer converter, the harmonics. We find out what's the harmonics or the spectrum of this. This current is, it goes first carrier frequency, but it's not, in the, it's actually sideband, so it's the frequency would be FC minus 3 F0. F0 is the fundamental frequency. So you can, and another one is the second carrier frequency. So you can see spectrum actually the one harmonics around the FC. So first carrier frequency, and then a second carrier frequency. We have done some study to cancel the first fundamental frequencies. There are 4 steps. So one step, essentially, what we're trying to do is just shift the carrier phase angle, okay, and then do some, I think, yeah, it's slowly. Essentially, what we're trying to do is the first step is to apply angle shift on the phase angle of the each leg of the carrier signal, okay, and also afterwards adjust the frequency according to the fundamental frequency. So we have to change the carrier frequency, okay, carrier signal frequency as well. And afterwards, we adjust the phase angle of the carrier frequency, and then based on the low bar, the bounds. So essentially, the 4 steps to go ahead, essentially, and what we're trying to do, you look at the right side is the spectrum change, and what we really end up with, is from the spectrum like this, and then you end up like spectrum like this. What we find out is the first carrier frequency being cancelled out. Okay, this is one study we look at, but the problem for these methods, there are few methods essentially. This is not finalized one. The one is the switching frequency is not fixed, which means the timer in the control, in DSP control, is quite difficult to design. And second one is the phase shift angle between the converters is quite difficult to manage. Essentially, you have a lot of converters on the grid might be difficult to manage as well. The other two I'm not going to cover, but what the student, what he's doing is try to focus on the second carrier frequency. So it's the 12C. What we're trying to do is you study mathematically, a lot of mathematics, and afterwards, really the results showing this, I think just jump all this through, is simplified everything. What you find out is essentially, if you can use the manipulate the modulation and you manipulate the power sharing of this two converter, what you find out you can essentially cancel all this second carrier frequency. Essentially, what's really happening is by simulation. I think this is simulation. So you find out the based on what you choose, you just shift the modulation signal by 90 degrees. What you find out is this second harmonic. I think it's the second harmonic. Let me check. It's a 30. Yeah, switching frequency is 32 kilohertz. So you find out here. I think there's something wrong here. It's 16 kilohertz actually. 16 kilohertz. We find out using these methods, we can cancel all these harmonics on the right side essentially. So, and this is setup of these students, and this is some experiment results. I think this is not final one anyway. Okay. Strange. What I want to show you is this is one. Sorry. I think what I really want to show you is the hardware we're trying to do. Okay. So this guy done quite a lot of hardware work. So this is the test rig. So you go back-to-back converter. You got the one is the big one. This one is the chroma. I think Jean-Paul probably knows this very well. The programmable AC source. So another one is using transformer. Okay, these two both to the grid. And these are two converters, and then of course get capacitor inside. It's Varec. So it's this students I think spend quite a few time to get this ready. And this breakdown, you see the converter, back-to-back converter, and what's in the middle is the capacitor. And you go FPGA DSP, which is Nottingham standard. If you go to Nottingham University, in our group, you can see this DSP FPGA platform quite standard one, fast to use. And then you go inductor, whatever, inside. There's some experiments out. I think I asked him to show me. Yeah, so what we're trying to do, this is the Fighouse test rig. So what we're trying to do is sum everything and put into like this way. So put into the cabin. Now actually what we're doing already is to put these 3 converters back to the cabinet, and then transformers as well, in the cabinet as well. So it would be very neat and nice for us to do further research essentially. And another thing we'll try to do is in this common DC bus, we probably have a kind of active filter which using the silicon carbide device or GaN device to be as a active harmonic injector. You can cancel all the these buses harmonics there. Okay, so I think we do need some good guy who can continue his work because he's now second year PhD. So in 2 years' time, probably finished PhD already. We're looking for some good guy who can continue his work. So if you're interested in this area, please talk to me. Okay. Yeah, I think this was what I wanted to discuss today. Actually, this is more interesting, I think. This is our building. This is a very nice aerospace technology center in West Nottingham. When it's sunny, it's nice. It looks very good. Okay, beautiful. So the shape of this building like aircraft wing. Very nice building. It's on the Jubilee campus. So we've been to Nottingham probably to see the Tower building is the old kind of it's a PMC main hub, but they're not branch of our group is in this building. It's set up in 2013. So Constanza spent most of her time here. Okay, yeah. So very nice building. Yeah, this is a little bit about our group. I think I forgot to mention this on the first day. We've got quite a wide spectrum of research, but mainly focused on the particles, machine design, and devices as well. So there's one. You talk about particles. There's one. I didn't mention there. Okay, this is one very important aspect of particles is the device itself. We all buy the devices, but this one very important part is how to develop the packaging of these devices. This is a very big piece of work in Nottingham University, and Nottingham University actually it is the center of the particles center in the UK. Okay, so it's for particles science I think we were leading university in this area. For application-wise, you have different application area. My main research, as I said, working on the aerospace side. But I mean, there's a lot of common things between aerospace, automotive, or or smart, even the marine, or the grid side. I think it's a lot of things you can do. In terms of money, also in terms of staff, we have actually it's 18 now, 18 professors, and then 45 postdoc researchers, research fellows, and postdoc, and about 65 PhD students. So it's huge. And then in terms of research grants, it's about 26 million pounds. I think the figure probably changed a little bit. Increased a little bit towards the end of the year. So lab-wise, we have more than 2,000 square meters lab. So it's an open lab. It's huge because we have lots of researchers and PhDs who will stay together essentially. So the power supply in terms of 1 megawatt is the power supply we've got. If you do the motor drives, we have different set of motor test rig, from the 1 kilowatt to 750 kilowatts. But this figure will be changed very soon because we are going to have a new PMC building. So PMC group, our group, will have our own building. Recently we bid the UK government funding, give us about 80 million pounds to set up a new building. So from end of next year or the after, we're going to move our own building to host all these people there. So if you get a chance to visit Nottingham, 2 years later, you'll be sitting in this shiny building. Very nice. I haven't got the design yet because we're going to present the design next week in our PMC group annual conference. Okay. So this is the 2 key parts. We've been doing a power density per converter, and this converter, this one, I think Gianpaolo probably knows this as well. So it developed 15 years ago. Is it 15 years ago? So 15 years ago per converter. The power density is already on that one is 20 kilowatts. Is that correct? Yeah, 20 kilowatt per liter. Yes. Yes. So it's 15 years ago. Okay. So we'll see. It was 50 years ahead any of other universities in the world. In terms of machine, I think this is one big chunk of work at the minute on the machine design side. One professor, Professor Chris Gerada, is the international internationally world leader in this area. The machine we designed come from several kilowatts up to megawatts. So that's what we are doing in a minute. Yeah, this I'm going to talk about this because the time thing. The Clean Sky, I talk about later a lot about Clean Sky, but in Clean Sky there are different blocks. Each block essentially is a work package, put this way. And Nothing actually evolve into all these different parts of the technology. For these three here, we are kind of co-partners in these three ITDs. So mainly for the technology demonstration. This top three is more like platform, which means different aircraft. You got fast speed. You got the fast rotor, fast rotorcraft, which means turboprop or helicopters. You got passenger aircraft, which can be large passenger aircraft, which means A320 types or A330 types, or regional aircraft, which is about below a 100 seat aircraft. I think this Clean Sky 1 stuff, I'm not going to talk about this. Let's talk about this already. So this Clean Sky 2, which from 15 to 2022. This is all the projects we got at the minute in the Clean Sky 2. The total money in the university level, about 37 million. I think it's increased probably about 40 now, 40 million in the university level. But not, PMC group, our research group, is about 20 million euro at the minute active. So we got lots of research opportunities to study in different areas in aerospace. So we go through slowly. So one of the projects called MNL is 5 million. The 5 million pounds, 5 million euro. Sorry, 5 million euro project from 2015 to 2022. So we recently have the annual conference for this project. This project looking at power converters, high power density power converters for motor drives. The machine size is looking at high power density machines. The different aspects for motor drives, essentially for the aircraft application. Another project to study models, SMART, to look at the environment control system for the modeling part for the regional aircraft, smaller aircraft. Because for Boeing 787, they already got the electric environment control system, but for the regional aircraft, they don't have yet. So this is some modeling activities. And the gains, this is another 5 million projects with different partners across Europe. You see, this project is to look at. So this project is to look at the new de-icing technologies for business jet. So Falcon is a Dassault Aviation project. It is looking at different aspects. In terms of material, you develop kind of new material which stop the ice accumulated in the aircraft wing. You develop kind of DC converter and management system to ensure that you can effectively de-ice or remove the ice from the wing. Okay, this is another. It's ongoing. It's until 2021. This project actually. So these three projects actually I listed here because we look at different aspects of the power system on board aircraft. As said, this is DC common DC bus again. So you look at the power system now in what you're looking at in the Clean Sky in the EU. They are all looking at DC grade. Okay. The three projects: Aspire, Astin, Enigma. So I listed them there. So we in the Clean Sky proposal, you always have acronym there. Aspire to look at the DC converter, which we're using the GAN device, the wideband gap GAN device, which is very small, can switch frequency, which goes up to 300 kilohertz. Power-wise, 3 kilowatts. Voltage-wise, from 270 to 28 volts. So STEAM is essentially to do the energy management. If I move one more down, so we have the DC converter, which DAB, that bidirectional, maybe have different ports, whatever. And then what we can do have converters connect to different buses. In that case, if one fell down, I can still use other DC buses, DC converters to supply power to the to my load. So this is done to STEAM, and Enigma is another project to look at the energy management when to do the power regeneration, essentially. So the three projects together put about 3 million together, projects, okay? So this work, we work with Leonardo aircraft in Italy. Yeah, it's quite interesting. All these projects just started last year, so it will be ongoing until 2022. And this another project currently I'm leading as well. So again, you see the DC bus, common DC bus here. So you look at what we look at, the device level. We're looking at the this kind of EPDC, the primary control center. Essentially, what is inside there is high power SPC. SPC is solid state power controller. Essentially, semiconductor switches. Essentially, and then you have low power side. It goes. So the high power side SPC, we're looking at 170 kilowatts or 90 or 50 kilowatts. Okay, so they are the very high power, and in the low power side, you're looking at 3 or 4 kilowatts. So DC converter here again, very familiar DC converter. We're going to use the silicon carbide device, about 4 kilowatts. The SPC on the secondary side it will be done by another partner, but again will be based on the silicon carbide device. So again, you see the gray side is DC bus, and then this is device level. Of course, in the project wise, we have to build up all the system in Northern University and test it, because the generation side we already have in Northern University, which is the AGAT project we talked about already, and afterwards do the energy management. And all this beauties, everything together, and then you can use the Clean Sky funding to build out the whole electric aircraft system in Northern University. And this is another project I'm leading at the minute. So it looks at the integrated drive. So it's ongoing. So next year we're going to. So essentially, it's a drive, okay? Machine, converter, control. And what we're doing is put into the aircraft gearbox. Very small area. The whole system, like this size, okay? But the length of like this size, the one pane. And then the challenge for this project is a very hot area because it is in the aircraft engine gearbox. So it's the temperature is 130 degrees, which the Partolyx doesn't really like. And also a very small area, so we have to deliver 20 kilowatts from this small system. You have to think about fault tolerance as well. So I have multi-phase machine. So this converter we already designed and tested only half of the system, okay? And then the whole system actually, the machine side, we finalized all design, thermal, electrical, mechanical, thermal, mechanical design, all done. And then it's actually it's in the manufacturing process. The converter, we finished all design. We tested the converter already. Only have to do just make a full circle, okay? Because this this system, you see, it is. So this is a shaft, okay? So the power converter, the machine and power converter will be like a very big hollow. Essentially, this is why you have a power converter. This is a big circle here, okay? Because at the end of the day, the big hole immediately. The converter will have a hole there to have a shaft go through. Okay, so this is very interesting project. The power converter is 40 kilowatts per liter. The power density is very nice design. So not in university we build everything. Okay, we design the machine, design the converter, build the converter, and test it, and then deliver to us to our partner. Okay, so this is the lab itself. The photo I took is actually 3 or 4 years ago. Now, actually, this area has been fully occupied. So this whole area, small area, is about 100 square meters probably. So got all the students that are working there, who are many dedicated to this projects I mentioned. So if you, Manuel, you want to come to Nottingham, yeah, you can base in there. And so what's really happening? So you look at the system-wise. This is what we have built in the lab. So we have the power generation source, okay, the AGAT system, and this will be another source we're building at the minute. One of my PhD is working on this, so it's called engine emulator. So we have aircraft engine emulator, and then you have two induction machine. One is high speed, one low speed. Low speed can go up to 20,000 RPM. Driving the so this engine emulator, they drive the two AGAT machine, and they supply DC power to here. Okay, so you have about 90 kilowatts there, and then 45 kilowatts there. And this DC source give you 180 kilowatts, okay, and all connect to the DC bus. And these two SPCs, all SPC will be from the INSTEP projects I just mentioned. And the DC converter, where is the converter? Somewhere on the map. The DC converter will be input from the INSTEP or from the Aspire project. So there are different projects can fit into here. And then the de-icing system, so will be tested in the lab as well. So this will be like load for the DC bus. What else I missed? And afterwards, of course, all these systems are connected together we're using the CAN communication to manage all this power system. And there's one dedicated students working on this. And we are using the lab view to do all the system level control. Okay, so it's very exciting, a place to work at, and we've got lots of very good researchers working together. And it's a very active lab at the minute. We've got loads of funding coming, and we actually have another project kick off next March to do the concept design for a real 19-seat electric aircraft with Germans. So it's a kick off next March. And also, we're having another project working on the SPC from April, I think, as well. It's another 1.1 million project. So got lots of funding there, and really want to have the top researchers come to Nottingham to work with us. Yeah, that's it. I think I spared 1 hour for you, Gianpaolo. Okay, I think probably can go for pictures, probably. Yeah, I mean, you really want to work with us because I found you guys. I mean, I was surprised. Gianpaolo was surprised. So how even the people who just finished the degree and the first year master, I think did a lot. I mean, compared with people in the. It's difficult to say in the UK. Yeah. Because I think you guys spent 5 years for your degree, but in the UK, it was 3 years. And I'm really surprised you guys really done a very good job. Yeah, you want to work with us? Yeah, let me know. Let Gianpaolo know. Okay, all right.